Okay, so we will discuss other issues with the regression model. We'll move on to heteroscedasticity. Remember, we made some assumptions about the error term, and I said before, if you have assumptions, then you need to, if you made assumptions, that means you need to test for those assumptions. So assumption 4. Should I wait? Are you still? So you don't need to answer all the questions, only the first and the second question. Okay? So, as I said, okay, the variance of the error term should be constant, sigma squared, or equal variance, which means homoscedastic, or homoscedasticity means that it's equal or constant variance. But this is unlikely to be the case with cross-sectional data. So it's very difficult to have, so whenever you have cross-sectional data, so you should assume you have heteroscedasticity, you have the problem, so the problem is present, okay? Because of the nature of your data, and in that case, that means the variance will be dependent on, you see, I, so it's will be different. So it's not going to be constant. So this one is sigma squared without the subscript. This one is sigma I squared, so with subscript I, meaning that it is actually a change. So there are so many reasons why you could have heteroscedastic error. So again, heteroscedastic error means here that error that doesn't have constant variance. Okay. So that could be because of outliers, or we use the incorrect functional form, or incorrect data transformation, or you make some observation with different measure scales. That is not, that could be one of or two of these reasons that cause the heteroscedasticity. So in this, I'll follow an example, the same example we followed last lecture, which is based on food data. I know some of you had some issues installing the package, the POE data package. I'll solve this in the tutorial today. I'll show you how to sort it out. So, for now, you still can follow the lecture and all the examples, and then in the tutorial, we'll see how to solve this issue out. So the main model here is we have food expenditure, how much an individual or a household spend on food depends on their income level. And if you remember, this was weekly data, and income here was measured by hundreds of dollars. So as you saw in the code last week, so you can give the regression a name, and then LM is the function, so linear model, and then you start with your dependent variable followed by this sign, and this your independent variable, and you tell the function where to find the data, so the data is food. So when I did this, and then I plot the graph, and I added the AB line, remember that was the regression line, this is what we have. So what do we have here? So how can I know this? This is likely to be heteroscedastic error. So you see the spread of these points around the line, the regression line. Okay? At low income levels, they are very close to the line. And as you go far from here, you move to the right. That means higher income levels. Then they spread more around the line. So here are very close to the line, and then they go like this. Okay? So that means the variance is not equal. So that means and as I said before, a minute ago, we said, if you have cross-section data, and this is cross-section data, okay? Because we have, why is it cross-sectional data? Because we have data about number of individuals or household in one point in time, so there's no time, okay? So there's no change in time, so there's no over time, it's only one point in time. And I have a large number of units, and that's why, so anyway, so in any time you have cross-sectional data, you should be worried about heteroscedasticity, okay? But you still need to test or find out whether you have heteroscedasticity or not. What did I do here? I actually plot the residuals, okay? So, do you see the error term? We don't see the error term, we don't know it, okay? So we take the residuals, which represent or a proxy for the error term. That's based on the sample, not from the population, okay? So what I did here, I just plot the residuals. Here again is income, and here again is y hat, or the fitted values. And again, it shows some sort of of pattern or some sort of not a constant variance. So then, what are the problems then? What is the problem of having heteroscedastic errors? Okay, the problem here is that you still have unbiased OLS estimator. Your OLS estimator is still consistent, but it's not efficient. So that means it's not blue. Okay, what do you mean by inefficient, or that an estimator that is not efficient? What do we mean by efficiency here? What do you mean by unbiased estimator? Unbiased. What does unbiased mean? So unbiased estimator, do you remember? Every time you take a sample, you get a value for beta. So if you repeat this many times, on average, these values should be very close or should be equal to the true parameter beta. Remember, we have population, we have sample. Okay? So what we're looking at here is the sample, not the population. So we didn't collect data for about income and household expenditure and food for all people in the UK, all individuals in the UK, all households in the UK. We actually have a very small sample. I think this was like 40 observations or something. Okay, so it's a very small sample. So this beta, or the value we'll get from this estimating that model, would be different if we choose another sample. But on average, so if you collect these values, and on average, so the expected value of this estimated parameter, beta hat, should equal beta, which is the true parameter from the population. When I talk about the true parameter, I mean the population. Okay? So how about efficiency now? So what do we mean by efficient? So what blue stands for? Best. That is best. Okay? What do you mean by best? It's all about the variance. Okay? That's the estimator with the minimum variance. Okay? So that's what I mean by efficiency. So an efficient estimator will have the minimum. That would be the best. We have the minimum variance among other estimators. Okay? So when I say here, okay, in the presence of heteroscedasticity, your errors will be unbiased, which is a good thing. We want them to be unbiased. However, they are not efficient. That means you lost the best. You lost B from blue. It dropped, and that's a problem. Okay, you remember we want these desirable parts of our estimator. We want it to be blue, and these that means that all the conditions we made from A1 to A7, remember, all the assumptions need to be true. So one of them fall here, one of them is not true, which is heteroscedastic errors. We want the error to be homoscedastic. We want the error to be constant variance, to have constant variance. But if they're not, then there's the problem. So your estimator remain unbiased, which is great, but it's not efficient, so it's not the best. Okay? And that's the problem. And what is the problem then when you have inefficient or not the best estimator? That means your standard errors are not reliable, and the decision you made based on this, the hypothesis testing, are not reliable as well. So how can I detect whether I have heteroscedastic or homoscedastic error? Remember, the first thing you think about, if you have cross-section data, so definitely, you're likely to have the problem, okay? But this is not enough. You need to see it, you need to test for it. So one way to do that, just plot your data, okay? Or, you should do both. You plot your data, because you need to know your data anyway, okay? And then you could plot the error as well. After you estimate the model, you plot the error. But then you also need to do the formal test. So there are two tests we'll cover today: the Bruch-Pagan test and White test for heteroscedasticity. I'll show you how to do them in R. Okay. So let me talk about the first one. So Bruch-Pagan test again. This is a test to apply to test for heteroscedasticity, whether you have heteroscedasticity or not. Okay, whether heteroscedasticity is a problem in your model or not. So let's say this is our model where we want to model some whatever phenomena you're looking at. So yi depends on x, i2 up to x ik. So we have k number of regressors, and then the idea here is that we're looking at the variance, and in that case the variance is a function of, let's say, of a number of x's, of number of these x's, let's say s. So if we have a constant or homoscedastic variance, that means all these alphas should be 0. And that's what we're testing for. Okay? So if we assume now, let's say that this function is linear, so we're just going to drop any other possibility, we just think of these as linear. So in this equation, my test statistic, or my null hypothesis, sorry, my null hypothesis would be that all these alphas equal 0. Okay? So, and the test statistics is n times r squared. So you calculate it by, this is n is the number of observation, r squared is the coefficient of determination, and that is a type here, so that should be follow chi-square distribution, and this should be the degrees of freedom, s minus 1. In R, it's very straightforward to do this. I'll show you how to do it in the tutorial, but this is the test when I produce this for the food example. What we found here is that the test statistic is 7.3. What we could do here is you could actually look at the p-value, which make it easier for you to make a decision. So rather than using the test statistic, compare this with the critical value from the chi-square distribution, and then make a decision, you could just look at the p-value. So when you look at the p-value, when p-value is very small, then you reject the null hypothesis. Very small, so you compare with usually 5%, significance level, 1% or 10%, okay? But usually most people look at 5%, but it could be at 10% or 1%. So let's say here, this one is very small, very, very small, so it's actually smaller than even 1%. So that means, what does that mean? I mean, you reject the null hypothesis. So what is the null hypothesis? That the errors are homoscedastic. So they are good, they are very well behaved. That's the null hypothesis. But if I reject that, that means they are not. Okay? So when you reject the null hypothesis with this Bush-Pagan test, that means you're, in this model, the errors are not homoscedastic, they are heteroscedastic. Okay? So what does that mean? The variance is not equal. So we should have equal variance, or we should have constant variance. So it doesn't change. So it doesn't depend on the individuals or the households. Okay? So in that case, it is a problem. So if we want to try white test follow a very similar approach. So you have again the residual square, so this is from the estimation, and then you regress this based on a number of x's or your regressors, but also it adds to this the x squared. So here I assume I have only 2 x's, so I didn't really, just to make it more like manageable, to be easy to present. So I assume we have only 2 variables, 2 regressors, x2 and x3. In that case, white test will be regressing this residual square on x and y, x and x2 and x3, the 2 regressors plus the 2 regressors squared, and then you multiply these regressors together. And then the test statistics is n, the number of observations, times r squared from this regression. And again, the null hypothesis is homoscedastic error, means constant errors means, well, we have the error that we would like to have. Okay, so if you reject that, that means there is heteroscedasticity. Okay, we already rejected that hypothesis with using Bush-Pagan test, and you're likely to have the same using white test. So as you would expect here, okay, so it's less than 5%, the p-value, so you can look at the p-value, and if the p-value, and this is for our example, food and income, so the p-value was small, and that means we reject the null hypothesis. Rejecting the null hypothesis means, what's the conclusion? Yes, thank you. Okay, we have heteroscedastic errors, or we have errors that does not have constant variance. Okay, that's assumption number, I think, is it 4? Yeah, we said this assumption number 4. Okay, so the question now, what is the solution? How to solve this? Okay, you could do something called, you could correct, because the main problem here is that when you have a non-constant variance that affect the standard errors, so you could correct the standard errors, okay, to account for heteroscedasticity, and that's exactly what we mean by consistent heteroscedasticity, consistent standard errors. And again, I'll show you how to produce this using R, which we call robust. So these are robust standard errors. So I want you to compare. So this is the same model, the food model. So I want you to compare between this estimation and this estimation. So these are one results, and these are the first results we had before. Okay. So this is what we estimated before. Now this is the new one with the consistent heteroscedasticity, consistent standard errors. So what's the difference? Look at the coefficients. Are they different? The estimates. Are they different?
No, the same.
They're exactly the same. So what's different? Look at the standard errors. Yes. And that's exactly what it did. It corrected the standard errors for heteroscedasticity. Okay? And that's what we have. So you've got the same coefficients, so it doesn't change the coefficients. So when you use this robust thing, so you correct the standard errors, it corrects the standard errors. So these standard errors are more robust, or account for, or take heteroscedasticity into consideration, and that's why this is more reliable. Okay? Is that clear? So should we say again to just summarize what we said? Okay, because this is everything we want to know about heteroscedasticity in this session. Okay, what is heteroscedasticity? Can anyone tell me? What do we mean by heteroscedasticity? You know, it took me a long time to be able to say it correctly. Heteroscedasticity, okay? I know some of you will probably struggle saying it for the first few times, but you get used to it, okay? So, can anyone tell me, I don't want you to repeat heteroscedasticity after me, I want you to explain what that means. What heteroscedasticity means. It's all about the variance of the error terms. Remember, we made assumption about the error assumptions, a number of assumptions about the error terms. Okay? So one of these assumptions is that the variance of the error term is constant. It doesn't change. It's constant. It's sigma squared. That's what we call sigma squared. It's just a constant. Okay? But what the problem is when the variance is not constant. Okay? So that's heteroscedasticity. So it's all about the variance of. You remember when I show you this graph, when we plot the data with the regression line. So the observations you see are very close here to, they spread like very close to the regression line. But as you go at higher level of income, then they become more spread. That's what I mean heteroscedasticity. And as I said, that is something. That's something that is likely to happen with cross-sectional data. Okay, so we know what heteroscedasticity is. How to detect or test for heteroscedasticity. Still making mistakes. So we cover two tests, Roche-Begen test and White test. What is the null hypothesis in both tests? That the errors are homoscedastic. See, I said correctly this time. Homoscedastic, or the errors are nice. They have all the desirable. They have constant variance. Okay, so they are homoscedastic or constant variance. If the p-value is very small compared to the significance level you're looking at, so if your significance level is 5% or 1%, and you find that the p-value is smaller, that means you reject or you not reject the null hypothesis. Yes, you reject the null hypothesis. Okay, and that means you have heteroscedasticity. In that case, you need to use heteroscedasticity consistent standard errors or robust option and that is something you can do in R, and I'll show you how to do it. And as a result of that, what we see, we get the same coefficient, the same estimation, but different standard errors. Okay.